Previously, we have discussed one path to class field theory, namely via abelian extensions of number fields. In our previous episodes, we have discussed how Kronecker generalized Dirichlet's theorems on primes in arithmetic progressions to express the density of the set of primes of Q splitting in a Galois extension K in terms of degree of K over Q. These theorems actually hold in a more general settings for finite Galois extension of a number field K, and a consequence of that is that the set of primes of K that splits in each such extension L completely determines L. This was a result by Bauer. Now in this episode, we want to prove this generalization of Kronecker using his theorems about the factorization of a polynomial versus its number of solutions modulo p. Recall that this theorem says that if f is a polynomial with integer coefficient, and if we define ap to be the number of roots of f modulo p, then we have that the average of ap is gonna be equal to the number of irreducible factors of f over zx. By the average of AP, we mean this expression here. Alright, so let's see why this implies that the set of primes that split inside a Galois finite Galois extension of Q must have density equal to 1 over the degree of K over Q. Now, by the primitive element theorem, we know that K could be generated over Q by some generator alpha. Now, let F be a minimal polynomial of alpha. Now, the key idea of the proof is to relate these different quantities, right? So, what's the relationship between the roots of f modulo p and the set of primes p that splits over k? Well, observe that for most prime p, f has a root mod p if and only if f splits completely modulo p, and that's if and only if p splits over k. Therefore, the density of the set of primes that split over k is equal to the density of the set of primes that f splits over. So now we just need to show that the set of primes p such that f splits into linear factor modulo p is just gonna be equal to 1 over the degree of k over q. So let's see why that is. Well, here by density we mean the following expression. And again, this is because we do not yet have prime number theorem, so we use Dirichlet's theories instead to capture density. So in the numerator here, we are summing over all the prime p such that f has a solution modulo p, whereas in the denominator, we are summing over all primes p of q. So let us see why this expression is equal to 1 over the degree of k over q. So we'll do that by showing that this fraction here, this density here, multiplied with k over q is gonna be equal to 1. So here's where we use the Kronecker's theorem. Remember, Kronecker's theorem said that this average of the AP must be equal to the number of irreducible factor of f. Now recall that we have assumed f to be a minimal polynomial, so f is irreducible over zx, and thus it has only one irreducible factor over zx. So this expression here, this average of the AP here, must be equal to 1. On the other hand, observe that when AP is not equal to 0, then it's gonna be equal to the degree of k over q. So why is that? Well, that's because, as we have said, so AP is not 0 if and only if S has a root modulo P. But F has a root modulo P if and only if F splits completely modulo P. Right? So in that case, then the number of solutions of F modulo P must be equal to the degree of F, which is just gonna be equal to the degree of K over Q, because F is the minimal polynomial of the generator of K over Q. Thus, we do have that when AP is not 0, AP is gonna be equal to the degree of k over q, and thus down here we see that we can rewrite this numerator as follows. So it's gonna be the sum over AP not equals to 0 of this degree k over q over p to the s. And then we can pull out this factor, this common factor, the degree of k over q, to get this expression here, which was just the density of split f, i.e. the set of primes that f splits over. So we see that this density multiplied with this degree is gonna be equal to 1 here, and so thus this density must be equal to 1 over the degree of this extension. But this density is just going to be equal to the density of the set of primes that split over k. Therefore, the set of q primes that split over k must have density equal to 1 over the degree of the extension k over q. Now, as a cute consequence of this, we're going to show that the n-cyclotomic polynomial is irreducible. Here we want to use the definition of the n-cyclotomic polynomial as the polynomial whose roots are exactly the primitive nth root of unity. We want to show that it's going to be the minimal polynomial for any primitive nth root. So let us let k be q adjoint a primitive nth root of unity, and let's say f is a minimal polynomial of zeta n. We want to show that f is actually the n-cyclotomic polynomial. Now, by Kroneker's corollary and by our previous discussion, we know that the density of the set of primes that f split over is going to be equal to 1 over the degree of this extension, right? Which is just going to be equal to 1 over the degree of f, because f is a minimal polynomial of a primitive element of this extension. But we know what this density is. Recall that the set of primes that f split over are exactly the primes that are congruent to 1 modulo n, and the density of this set is just going to be equal to 1 over phi n. And by phi here we mean the Euler-Phi function. So then here, equating this, we see that then 1 over the degree of f must be equal to 1 over phi n. In particular, the degree of f must be equal to phi n, i.e. equals to the degree of the n-cyclotomic polynomial. But f must divide this n-cyclotomic polynomial because this n-cyclotomic polynomial vanishes at zeta n, whereas f is the minimal polynomial of zeta n over q. So since both of these polynomials are monic of the same degree and one divide the other, they must actually be equal. In particular, this means that phi n, the cyclotomic polynomial, must be irreducible. Up next, we are gonna give an even more abstract generalization of Dirichlet's theorem. But for that, we'll first need a generalization of the ideal class group.